to applications. Here we go. So what you're looking at here is essentially, oops, there we go. Is essentially a basic type of question that happens in applications. We've got a function, secant x. A equals 0, doesn't that basically means it's Maclaurin series? We're only going to use two terms. That means n equals 0 to n equals 2. And the x values are going to be between negative 0.4 and positive 0.4. You're going to be asked to find the Taylor's polynomial T2. And over here, I've got two versions of it. The Taylor's polynomial with an n below it means that you use this formula here and you stop at n. Well, if you were doing a T2, wouldn't the formula just be those three guys? And it is possible, isn't it, that one or both of two of those terms could in fact be zeros, right? So a T5 of x might only have three terms in it because two of them are zeros, right? If you're doing a number that's not zero, then this is the more general version of a Taylor's polynomial. So first thing they ask us to do is to find T2 of x. Well, I know that's going to be f of 0 because of this guy, f dashed of 0, x, over 1 factorial, and the second derivative at 0, x, over 2 factorial. So I'll set the working in motion here. And you need your differentiation cap on. You need to go back to the mists of, oh God, what would that be? 6 months ago or whatever, whenever you did Calc 1. And remember the derivative of secant, which is one of the least common ones. Most people remember the derivative of sine and cosine, but they're a bit rusty on secant. Okay, tell me what it is.
Secant times tan.
You nailed it. Secant times tan. And I need the second derivative as well. Why do I need the second derivative? Because when you do a T2, don't you stop at the second derivative, right? If you do a T4, you stop at that. How do I know it's a T2? They just call it n equals 2 here. That's how I know it's a T2 they want. Now, this is going to be an FG, isn't this going to be a product rule? So f dash g plus f of g dashed. If you differentiate a secant, you get a secant tan. Leave the other one alone, which is just tan. Plus leave the first guy alone. And what do you get if you differentiate a tan? What's that going to be? Now, I know the midterm is an open book and you can go and hunt for it. But if you have to go hunting for everything, you'll never finish the test, will you? So what is the derivative of a tan?
Secant squared?
Correct. And tidying up, secant squared, oops, secant tan squared plus secant cubed. And now we need to find the value of the function at 0, the first derivative at 0, and the second derivative at 0. The secant of 0 is the same thing as 1 over the cosine of 0, and it's 1. The secant of 0 times the tan of 0. What number is the tan of 0? Tan of 0.
Just 0.
Right. So won't secant times tan get you 0? Now the second derivative is 1 times nothing. So that's just nothing. Plus 1 cubed, which is 1. So what we have here is this guy's 1, this guy's 0, this guy is 1. So when I set up my solution to the Taylor's polynomial T2, it's going to be f of 0, f dashed of 0, x over 1 factorial, second derivative 0, x squared over 2 factorial. Now that guy's 1. This guy's 0, so I don't really care about the rest. You know, if some 0, isn't the whole thing going to be 0? And then this fella here is 1 again. And of course, you shouldn't leave things like that. You should tidy them up. So how about that guy? So T2 of x is 1 plus a half x squared. Do you notice that the x term is gone? That's not uncommon for these questions for you to lose a couple of terms. So far, so good. Now, the next piece of the puzzle is phrased like this.
Sorry, Professor, could just real
Yes.
quickly, is that
Mhm.
just secant tan squared x?
Yes,
Plus,
it's
okay,
just secant.
making sure.
Yeah, I put a 2 there before I realized it was only one of them, right? So it's a secant tan squared, which still ends up being 0, but you know, for the reason that it's that guy. Now, when you are asked this, what they're really asking you for is, what is the maximum value of the remainder function, which is that guy. Now, the remainder function, also the error function, is f of x take away t2 of x. So in this case, it's the secant of x take away this guy. And if you remove the brackets, you get that guy. So far, so good. Now, we are being asked to find the maximum value of this guy. Now, the way that you're going to do that is at the end of yesterday. Do you remember when we did a guy yesterday? The original curve looked like that, and the T3 or the T4, whatever it was, kind of looked like that, right? And the error, which is essentially what the remainder function is calculating, is how far away from the real answer are you going to be? And don't those happen at the extreme sides? So in this question, can you imagine that's negative 0.4 and that's positive 0.4? So if you want to find the maximum value of this function, don't you need to just calculate two things? What the value of the remainder is at the two endpoints. Does the logic of that make sense, that the most error is going to be happening at the ends, right, the furthest away from 0? Right? Bobby, question? No, just the thing highlighted, it looked like you were going to. So I'm going to evaluate this at that number and this at that number. And whichever one of these is the biggest, and I don't care if it's a negative or a positive, which is basically all that absolute value is doing, then that's going to be my maximum error. And so it's really a calculator job now. And I go into mode and I make sure it's in radians. And now I'm good to go. If you want to find the remainder function at, oh, and you're wondering where the negative 0.4 came from, it was in the question, right? It was from this to this. So I'm going to do the secant, which is basically, from scratch, 1 divided by the cosine of negative 0.4. That's how you get a secant, right? 1 over a cosine. Take away 1, take away a half of negative 0.4 squared. And the answer I get is 0.0057. Oh, they want 6 decimal places, so 704 then, right? Now, I'm also going to calculate it at this side, and I'll see what I get this time. So if I just do second answer, I can go back and I can delete that guy. And that's it now, 0.4, and I can delete that guy. I'm just being lazy because I don't want to type it all. And the answer I get this time is 0.005704. They don't always end up being the same number, right? My guess is that this function is very symmetric, right? So the bit at the left and the bit at the right are pretty much the same guys. So if you wanted to know what is the maximum value that this function's error is going to be, it's that guy. So what would that tell me? Wouldn't it tell me that if I used this quadratic, if I used this quadratic here, instead of the secant function, and I only used it for values of x from negative 0.4 to positive 0.4, couldn't I guarantee my answer is good plus or minus that number? In many cases, it'll be a lot less than that. Are we cool with that? Right. Now they go on and they say, check the answer by graphing R2 of x. So that's what I'm going to do. I'm going to go to Desmos. Hopefully I've got it somewhere handy. God, these windows are everywhere. Where are you, Desmos? I know you're hiding. Okay, I got you. Oh, shooting space. You notice I didn't swear there. I'm really good at not swearing. Right, so the remainder function was secant x. So I hope this guy understands secants. Otherwise, I'll have to change it. Yeah, it looks like it does good. Take away 1. Take away 1/2 x squared. So what's that? 0.5 x squared. And we are only interested, so here's a little trick, curly bracket, negative 0.4 less than or equal to x less than or equal to 0.4. Somebody showed me that little trick. Don't worry about the fact you can't see anything here. That's just because the error is so small. There. Can you see how good the error function is? Can you see how little error there is? Would you also agree that the worst case scenario is here, right? The higher up, the more error. And can you see that little symmetry thing? Now, if you wanted to see this a little bit clearer, you can go here and you can tell it to do the y values in a range of numbers that maybe are a little bit smaller. So how about 0, 1 on this side and maybe 0.1 on the other side. So Desmos is really cool. There. How about 0.03 then? Okay, clicker. Do you get a better view of the error if you just change the scales? And I bet you that that distance there is the 0.005704 that we calculated a minute ago. That makes sense. That's the remainder function at that value. Are we good with this new guy, the Rn, the R2 of x? It's basically a function that will tell us if we use a Taylor's polynomial to approximate a function, that the R2 will tell you the error. And that's how I do that question. This is how you would do it in a more theoretical way. R2 is the third derivative at C, absolute value, x to the power of 3 over 3 factorial. And who's this little guy called f triple dash 3? Well, it's obviously the third derivative and it's the maximum value of the third derivative in the range this fella to this fella. So if you wanted to do this question, wouldn't you have to find the maximum value of the third derivative? And then what would this guy be? This guy would be 0.4 or negative 0.4. And this guy would be 3. And you notice that for an R2 error, everything's in 3s. For an R7 error, these would be the 8s. You are still going to get, well, apart from the fact that this is downright ugly, isn't it quite difficult to know what the maximum value of a secant function is between negative 0.4 and positive 0.4? And I'm not even sure it is a secant function, because by the time you get to the third derivative, isn't it a much uglier version than that? Can you see why I do not do that technique? Right? Unfortunately, and I mentioned this at the start yesterday, WebAssign does not do it that way, right? It does it this way. And when it does it this way, the answers are different. And you are not going to pay any attention to that. You are going to get used to having the wrong answer for this guy, according to WebAssign, right? And I will just give you the points back at the end, so you won't lose anything. But I don't have the ability to change what WebAssign thinks is the answer, at least I don't know how to do it, or even to change the question so that it would do it my way. So we would be putting in, I've forgotten my answer now. Oh, we would be putting in here 0.005704. And in here, they give you like 4 pictures and you pick the one that looked like that. Right? So I'll say it one last time, because somebody's going to shoot me an email and saying, I don't know how to do these. I keep getting part B wrong. And I've done it exactly the way you said, and WebAssign, and I've used 5 guesses and it still says I'm wrong. Right? That's not going to happen. Agreed, Kira? You are not going to send me an email saying, this is not working. You told us it should be this number and it ain't. Would you agree that what we're doing here is approximating an error? And mine is an approximation as well, because isn't it only as good as my calculator? But if you did this one, isn't this bit an approximation as well? You know, what's the maximum value of a third derivative? Well, how do you know it? How do you even calculate it in lots of cases? Unless it's a very primitive function. I guess you can do it then. Are we comfortable with that question? How that one kind of spanned out? Any questions about it? Okay, that's good news. So let's just move on. Question 5 is just like question 4. Same process, same guy. What's this one? Okay, question 6. Same type of question, just a little bit different. That's why I'm doing it. The function is going to be e to the x, my favorite. A is going to be 1. In this question, you are only being asked to find T3 of x. So this one doesn't have that remainder bit or graphing bit, right? So it's going to be a little bit quicker. Here it goes. Since you want T3 of x, the first derivative is that, and e to the power, whoops, jumped ahead of myself, f of 1 is e. The derivative of x is e to the x, f dashed of 1 is e. Can I just cut to the chase? Would you agree that every single one of them is an e? Because it's a nice, easy question. So T3 of x is going to be this version, because it's centered at 1. So it's going to be f of 1 plus f dashed of 1, x minus 1 over 1 factorial. Oh, by the way, at the end of this, you're going to be told something really, which I think you'll like. So since it's a T3, don't we finish at the third derivative, and so on. And so it's e. It's e times x minus 1 over 1 factorial plus e x minus 1 squared over 2 factorial plus e x minus 1 cubed over 3 factorial. And here is T3 of x. Do you think that you're going to have to FOIL all of these out and collect them together and make a polynomial, like so many x squared, so many x cubed, so many x's and plus a number, right? That kind of thing. Now here's the good news. It's finished. Taylor polynomials are left alone. And so you leave them as x minus 1 cubed and x minus 1 squared. Was that right? Are you like that answer? That you do not need to FOIL these out and collect like terms. Taylor's polynomials are in standard form. That's the way you write them. Now, I'm not doing it, but couldn't we put in e to the x and it would look like that? Couldn't we put T3 of x and it would look something like that, wouldn't it? It'd be a pretty good fit, but a little bit out. And they have 4 pictures and you pick the one that looks like that, right? So that would be the second part of this question. First part, find him. Second part, check it by graphing as they describe. Question 7 is the same as question 6. Only in question 7, it's a cosine function and it's a T3 of x again. I think I want to do that then. The next one is, I guess I could do one. And this one is just like 6, 7 as well. This time the function is an actual log and we're being asked to do it at 1. And what one have we been asked to find? T3 of x again. Okay. F dashed of x is 1 over x. Second derivative of x is negative 1 over x squared. Third derivative of x is positive 2 over x cubed. This guy evaluated at 1 is 1. This guy evaluated at 1 is negative 1. And the third derivative evaluated at 1 is positive 2. And this guy here, if you evaluate him at 1, is 0. Okay. So T3 of x is going to be that guy. So it's going to be f of 1. The derivative at 1, x minus 1, 1 factorial. Second derivative at 1, x minus 1 squared over 2 factorial. And lastly, that guy. And what do I get? I get 0, so I don't really need that. I get 1, x minus 1 over 1 factorial. I get negative 1, x minus 1 squared over 2 factorial. And I get plus 2, x minus 1 cubed over 3 factorial. Probably didn't need that line. That guy gets you x minus 1. This guy gets you negative 1/2 x minus 1 squared. And that's 2 and that's 6. So you get a third x minus 1 cubed. And you get that. And you can plug that guy into Desmos, and you can plug this guy into Desmos. And if you do a log function, it looks like that. And if you do this thing into Desmos, it probably look, well, maybe something like that, right? It'll be close, but it won't be perfect. So if I give you a function f of x, and I ask you to find T3 of x or T5 of x, and I want you to do it at a equals 1 or a equals 0, Are you comfortable about the process? We're good. And if I said sketch the original function and your T3 of x and look at the comparison, you are good. What would happen if I put in my original function f of x and it looked like this, and I did my T3 of x and it looked like that? What would that tell me?
Well, either it's like centered way off to the left, or
Oh, that's
you just
possible.
did something wrong.
Yeah, I was getting at you did something wrong. When you do a graph, shouldn't you center it on whatever the A is, right? So if A is 0, 1, or 2, you should probably center your graph on that. Yeah, you're right. It could be that if you went away over here, it was a great fit, but this is miles away from it. That was also a possibility. Oh. They don't cover this, but I think it's an important thing in general to know, even though it's not an exam thing. We said right at the beginning that the function that you're going to do all these Taylors and Maclaurin series for had to be well behaved. And well behaved just meant nice curvy curve, right? Nothing weird going on. What do you think would happen if I tried to do a Taylor series of a function that had something weird in it, like a vertical asymptote, for instance?
You would end up adding infinity.
Well, you could end up, if you centered it on that, you'd end up adding infinity. If you centered it, say, at this point here, what would happen? What do you think would happen? Do you think it would be a pretty good fit to that curve? It's going to be a pretty good fit there. And then it'll do a little baby drift. But when it gets to this place here, all bets are off. The polynomial, won't the polynomial do what polynomials do, right? Polynomials do not shoot off to infinity anywhere, do they? So if your function has something bad happening, something that's not well behaved, shouldn't you be really careful about estimating the value of the function anywhere near a vertical asymptote? Here's another function that causes extreme problems. Cube root of x is not a particularly horrible function. It has one really bad problem. I haven't drawn it very well, but do you know x equals 0, it's got a vertical tangent line? If you did a T3 of x for a function that has a vertical tangent line, if you try to do it at the origin, you'd end up with infinity, right? One of your answers would be 1 over 0, right? You'd be screwed, right? You couldn't do it. So if you centered it, say, here, it'd be pretty close here. And then it wouldn't do a very good job anywhere close to 0. Can you imagine what's going to happen is that it's going to do a polynomial, and polynomials don't go vertical tangent lines either. So if you ever try and do a Taylor polynomial of a function, you have to be extra careful that it doesn't have some weird stuff going on, because you could get into the habit of saying, yeah, if I do a T20 of something, it's a really good fit. Do you know a T20 for a vertical asymptote is still useless here? But you're not going to notice it because you didn't bother to graph it, or you never even thought it was going to happen. Or in the case of a vertical tangent line, you would look at it and superficially you say, nothing weird going on here, so I don't need to worry about it. I'll do my T20 and I'll get a really good approximation. And then you plug it in and you think, why is my answer 14 times bigger than it should be? Well, because there's something weird going on with your functions. So that's what well-behaved means. But every question you've ever been given is well-behaved for that reason. Right? They do what they should do. Right, let's do another one of those. Yeah, we've got time. R2 of x's and things. In this case, this is going to be a version of question 10. So the function f of x is 2 over x. It's going to have n equals 2. It's going to be centered at 1. And it's going to be 0.6 less than or equal to this guy, less than or equal to 1.4. This function has a problem at 0. Agreed? Can you see why they kept well away from 0? As long as you keep well away from the problem, you're probably safe. It's only when you get close to the problem. I wouldn't use this for 0.1 to 1.9, for instance, because isn't 0.1 getting dangerously close to there? Right, so I have f of x, which is 2 over x. F of 1 is 2. The first derivative, oh, by the way, I'm finding t2 of x because of that. That's negative 2 over x squared. The derivative at 1 is negative 2. The second derivative of x is positive 4 over x cubed. Second derivative at 1 is 4. So my t2 of x is going to be f of 1. The derivative at 1, x minus 1 over 1 factorial. And the second derivative at 1, x minus 1 squared over 2 factorial. I'm just writing down the terms that you need for a t2, centers at 1. This guy is 2. This guy is negative 2, x minus 1 over 1 factorial. And this guy is 4, x minus 1 squared over 2 factorial. So what does that get me? 2, take away 2 lots of x minus 1 plus 2 x minus 1 squareds. Quite comfortable with that? It's kind of plug and chug now, isn't it? Find 2, 3 derivatives, evaluate them at whatever number they say, plug them in here, tidy it up a little bit. That's your answer. You don't need to do any more. That's t2 of x. So let's find the remainder function, r2 of x. R2 of x is f of x, take away t2 of x. In this case, 2 over x, take away all this. So it's 2 over x, take away 2, add 2 of these guys, take away 2 of those guys. Are you comfortable with how to find the function r2 of x? Now, we're going to find that guy. That's how it's written. What that is basically, we want to find the maximum value. Now, in this question, we're going to find the remainder at 0.6 and the remainder at 1.4. And won't the biggest answer be the maximum error, right? Because this is going to be what's happening at the ends. So at this point, well, what will this one be? This is going to be 2 over 0.6. Take away 2 lots of 0.6. Take away 1. Take away 2 lots of 0.6 minus 1 squared. And I wish I hadn't done that because it's so big I can't write my answer, but here goes. 2 divided by 0.6. Take away 2. Add 2 lots of 0.6. Subtract 1. close the brackets. Take away 2 lots of 0.6, take away 1, close the brackets, squared, and the answer I get, I'll have to put it up here, is 0.21 and lots of 3s. You do this version, 1.4 version, it's going to be 2 over 1.4. Subtract 2, add 2 lots of 1.4, take away 1. Subtract 2 times 1.4, take away 1 squared, and the answer I get is negative 0.091428 and some stuff. So what, between these two numbers, what is the maximum error going to be?
.213333.
Yeah. Don't care if it's plus, don't care if it's minus, don't we just care how big it is? That's why the absolute value is there. So if I used this polynomial for the function 2 over x, and I only used it for values of x from 0.6 to 1.4, can I only guarantee that my answer is correct to plus or minus 0.2 roughly? Would you agree that's not very good? I mean, an engineer could live with that because they're not very good at counting, right? But normal people would say, I don't like that. What do you think the problem with why I'm getting such a big error? Whereas in most of the other questions, the error was, nothing point, nothing, nothing, 3 kind of size. Why is this one so big?
Is it because we only went to 2 terms? Probably that third term would help a lot.
The third term would help a lot, and that's a truism. That's true every single time. What else is causing that problem? And it's specific. Say again?
Is it because the like the 2 over x, like you're pretty close to that 0 like asymptote?
Yeah. We're just a little bit too close. It's like you get too close to the sun, you get burnt, right? If you get too close to something bad happening in a function, the errors become really big, right? So evidently, I thought 0.6 was okay. Maybe it should have been 0.9, right? That would have been a lot nicer, right? That would have been, But if you center it at 1, aren't you kind of close anyway? You really should center it at 2 or 3 if you wanted to be safe. And the last part of that question would be basically plug this in, right, and sketch it. And I want to I'm curious, I want to see how bad a fit that truly is. So I'm going to try and find, I can't find it now. Where are you? I know you're in here somewhere. Right, let's find Desmos. There we go. Now, there is a third possibility, it has just came to me, but nobody's pointed out. Couldn't I have screwed up my T2 of x? Couldn't one of them been a plus instead of a minus, and that might have caused the trouble? I mean, that's a third possibility. I'm hoping that's not the answer. So I'm going to go here, and I'm going to do our function, which is our 2 over x guy. And then it is take away 2. Then we're going to add 2 lots of x take away 1. And then subtract 2 lots of x take away 1 squared. And the restriction was 0.6 to 1.4. So 0.6.
Mr. Robertson,
Yes.
the 2 from the square didn't actually get put in.
Oh, it didn't get put in. Thank you. There we go. Right, let's just check anything else missing here. Looks good. So why is my function not appearing?
I think you're too zoomed in.
What's wrong?
I think
Zoomed
you're
in the right
zoomed in
place.
too much.
Oh, it's just a zooming thing. Ah, of course. Look at the size of that window. Oh dear. Can you see the error on the 0.6 side? Do you see it shooting up like nobody's business? Didn't it just get too close to the sun? Right, temperature really got high, the error got big. If you look at the other side, isn't that a reasonable distance? I mean, it's still not great. What kind of functions, and it's just a random question, what kind of functions do you think Taylor polynomials work well with and give very accurate answers? What do they look like if you drew them?
Would it be a parabola?
Yeah, anything like a parabola would work. Wouldn't any function that's just a nice curvy curve to it, right? Those ones work really well because aren't polynomials just curvy curves themselves? By the way, that is not something you can look up on the internet. That's just what I've called it, right? They're just curvy curves, right? You do not want functions to be straight lines. Would you agree straight lines don't work very well? So if a function is really straight, you're probably going to have a problem with it, or at least if it's straight and then it curves, you're going to have a problem with it. I guess you'd be okay with straight. Can you just call it y equals 2x and be fine, right? Don't have vertical asymptotes. Don't have vertical derivatives, right? Don't do oscillations. Now, do you know the ones I'm thinking of are the ones that go gentle and then they go da 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 da. You know, like the sine of 1 over x. Would you agree that would be a bad one to try and do a Taylor's polynomial on? Because it changes height very quickly towards 0, doesn't it? Some really bad happens. And those would be examples of those. But there are a lot of functions in the world, aren't there, that are just nice curvy curves. And they are good. So what we got? We've got a few more minutes. Perfect timing to finish this one. So moving on to what does question 11 look like? Well, we've already talked about question 11. The function that we're going to do, in this case, it's going to be what a t3 of x, is the function the cube root of x. They actually called it x to the 1/3. And you're going to do it from 0.9 to 1.1. Where does the cube root function have a problem as far as Taylor is concerned? Mentioned it already. What's the weird part of a cube root function? Yeah, that's a better version of it. At what value of x?
0.
0.
Right. I'm hoping this time that 0.9 to 1.1 is far away, you know, it's far enough away from the 0 for it to have no effect, right? If it was like 0.3 to 1.7, I'd be a bit more worried, wouldn't we? Because we'd be getting near the danger zone, right? So that one would work perfectly fine. And you're going to do the usual T3 and find the remainder of 3 and then graph it. So nothing to see here. Question 12, you're going to do the same questions to that function, and it's going to be at a equals 1. And the interval of x is 0.5 to 1.5. This function has a problem, but it has a problem actually when you get to x is -1/2, because that makes the log of 0. This one I'm pretty sure is fine. I don't have time for 13, but it is the last one, so I can at least get you started on it. For the final question, you have x natural log of 2x. It's going to be centered at 1. You're going to do a T3, and when you're finished, it's going to be in that range. Right. I'll write it down here because I need more room. The value of the function at 1 is just 1 times the natural log of 2. So the answer is natural log of 2. the first derivative is going to be a product rule, f dash g plus f of g dashed, and there's going to be some of you are going to make this mistake. So derivative, leave it alone. Leave it alone. And then you're going to differentiate that guy, and you're going to write down 1 over 2x. And that's going to be the mistake. What is the full correct derivative for the natural log of 2x?
1 over
If
2
you think,
times 2.
yeah, isn't it a chain rule? So you need to do a times 2. So what you in fact get is the natural log of 2x. That cancels with that, and doesn't this cancel with that? And whoa, you weren't expecting that, were you? Now, are you okay with the derivative of the natural log of 2x is 1 over 2x times the derivative of 2x? That's where this 2 came from. Now, if you do the second derivative, you're going to get 1 over 2x times 2 again, and that's going to get you nothing. So the second derivative of x ends up being 1 over x. This function is going weird places every time, isn't it? And then lastly, the third derivative of x is just negative 1 over x squared. So if you evaluate the function at 1, you get this. The derivative at 1 gets you the log of 2 plus 1. The second derivative at 1 gets you 1. And the third derivative at 1 gets you negative 1. So they're quite interesting numbers. And when you go and you plug these guys into, there's my guy. These 4 numbers are going to go here, 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 and here. And you don't need to do any tidying up. It's okay for an answer to be the natural log of 2 plus 1 in brackets x minus 1, over 1 factorial. It's okay to be called that, right? So you don't need to distribute, FOIL, factor, or any other phrase I can think of. Just leave it alone. The only thing you should really take care of, isn't it, is the factorials, right? Because you might get some cancelling. Say your last name and bye-bye. And I am getting really good. That is bang on 9:50. And we'll see you tomorrow, where we get to see parametric equations and curves.
Professor, could I look at problem 13 again?
Probably. I shouldn't throw things away so quickly, should I? Here we go.
Thank you so much.
Can I ask a quick question about one of the homework problems?
Sure, that's what I can do right now. So I'll put that one over there for those who are still copying. What's your question, Kira?
Okay, so it is from the 11.10, the Maclaurin-Taylor series set.
Is it easy to tell me out loud, or will I need to look?
Yeah, it's super easy to tell you out loud.
Okay, go for it.
So it's just f of x equals 5 cosine squared of x centered at 0.
And what do they want from you?
So they just want the first 4 non-zero terms.
Okay, so I'm going to rewrite this guy for differentiation purposes. Like
The
that.
thing
Some
that's
people
messing
don't
me up
need-
is I reference the notes, I reference the problem we did in the other, and I swear I've plugged into my calculator 40 times, and no matter, and it just
Did you
won't.
have radians? Let's go for the obvious mistakes.
Didn't really matter on this one because it was just
you're right.
cosine of 2x.
0 in both units. You're right. It doesn't matter. Okay.
Yeah, because it's just cosine of 0.
Right.
Yeah.
Let's
Good one though.
right. Let's look at this guy as a chain rule. So 5 cosine x squared, you get 5 times 2 cosine x's times the derivative of cosine x, which is negative sine x. And that gets
Which is just
me
the negative 10 sine of 2x.
Well, it is, but I'm not actually going to do that because I'm using a trig identity. I'm just pulling out the negative. Do you recognize 2 sine x cosine x?
Yes, because then that merges into just the sine of 2x.
Right, and the advantage of doing that is that for the later derivatives, much easier to differentiate.
Oh, I missed something so obvious. That's what I was worried about. I put 10. I kept the 2 there.
And then the thing just
And
keeps
then the
on
whole
growing
thing,
like
it
some
just-
horrible monster, right?
Yeah, and all of a sudden it was negative 320. And I was like, whew, that escalated quickly.
Right, so
Okay, I just need to plug in 5 and do exactly what I did. Okay, I'm good.
you good?
Thank you.
Not a
Gotta
problem.
keep my trig identity reference sheet a little closer.
Yeah, you know that in the midterm, you're going to have a pile of paper this high. So try and memorize as much as you can so it's only this high.
Yes.
Because you know you're going to look at something and say, I know what that is, but where did I write it down?
Yeah. My sheets are pretty organized, but you can only do so much with that many formulas.
That's it. There is so many things that you need to know now, isn't there? All these little trig identities, algebra tricks,
It's a lot.
what the secant of something is, you know, what's the derivative of tan, you know, all these things. And yeah, they add up. They add up.
Yeah. Okay, sweet. Thank you. Have a good rest of your day.
You too. Any other questions, guys?
Yeah, I had a question about number 8.
Is it easy to write down again?
We did it in class.
Oh, that one. Okay. I have it somewhere handy. Here it is. Right. What was it about it that wasn't making sense?
So in the final answer, I think it just got copied down wrong. The 1/3 term.
Uh-huh. Right.
Oh, I see it. Never mind.
Right. That's 6. 2 over 6 becomes a third.
Okay, gotcha. Thank you.
Okay. Not a problem. Any other questions from anyone? David?
About the test this weekend.
Yes.
The weekly tests are supposed to be practice. How are we gonna be able to see the score before we have our midterm?
That is a good question. I'm trying to think of the solution to that. Because we have to hide them after the event. What do we need to hide them? No, I guess I don't need to hide them. Once the clock kicks in, right? Once midnight happens, you can't change it. So I just need to make sure that I make it visible all the time. So you'll be able to see it. It will automatically grade your answer. But you know that I have to go back and check it because I always end up finding some things that you should be given points for. I can guarantee, for instance, that won't you have a couple of those maximum R3 of X's? Right, because they'll do it one way and I know that you should do it the other way, so I would be fixing those. So if your question is how will we see it, I'll just make sure that it stays open so you can see it. But will you bear in mind that the score that you get might be changed once I have a chance to grade it. And I won't be able to grade it because I have to wait till midnight when you're all finished and I'll be sleeping. I hope by midnight. Hopefully you lot have finished it before midnight as well because you want to get plenty of rest. Does that answer your problem?
Yeah.
So the score you get, the one that you end up getting will be better probably than the score you see in whatever sign, especially because of some of the issues that we have in this sector. Right, any other questions?
That'll be same for the statistic class too, right?
Yes, same for the statistic. I should do it for all my classes, so that means I'll do it for all 5 of them.
Okay.
Right, Dave, do you need a time issue? Do we need to deal with that? Because the answer to it is you just keep going. Right, so if we do a time issue thing, they're going to, you'll notice, I guess I should have told you this, that there are going to be other people from other classes coming in and dropping out because they started at times that you might still be working. So don't worry about that. So people will be here all the time, right? Coming in and going out depending on when they start the exam and when they would finish it.